right, so this is the lecture for HVR110, week 3, lesson 2. We are going to be getting into chapter 9 in your electrical book, talking about components for electrical motors. All right, so electric motors, they have they're going to be the main thing that makes everything move that we have. We've been talking about this. You guys have been learning about motors, working with motors. They're the one that's going to allow for airflow to take place, for refrigerant flow, for water, for our transfer of heating and cooling. Because the main thing we have to understand is we can't, we're not going to be making a place colder or hotter. What we're going to be doing is we're going to be moving heat always. So when we have a furnace operating, it is having a fan motor that has many switches on it to make sure that the fan is operating properly and that it gets the exhaust gases out of the structure safely, so that nobody's choking on a bunch of carbon monoxide, which is less than ideal. So the main thing to understand is understanding the components for these electric motors and understanding the parts and things that make them run. That is going to help you out greatly. It's not so often that the motors go bad. There are ways that we can test them, and that's what we're going to talk about a little bit today. There are ways that the motors can fail, for sure. But it is more common to see the smaller parts that are doing more of the work, that are basically going to be taking on more of the load. They're passing power through them more often, and usually they're smaller little cheap parts. There are contactors, our relays, our sequencers. They're passing through a lot of electricity, but they're a really good control. They're easy to access most of the time. Most of the time, I say, with a little bit of caution, just because there are plenty of times I've had tough to reach spots for relays and contactors and all the sort. But they are your main way that you're going to have controls in the system, and they're going to allow for your motor to properly operate, so that you don't have to worry about a motor failing all the time. Instead, it's going to fail a cheap little electric component or part. So that's what we're going to look at mostly today. So starting relays for single-phase motors. Again, single-phase motors, remember, you only have to have 3 things as far as wires going to them. You need a common, a run, and a start. Now, these relays, they're going to be your main thing that's going to actually start up your motor. All right, there's a couple of different styles of them depending on what kind of motor we've got. But talking about with this one specifically for single-phase, you've got it where it's going to has to have a means of dropping the starting winding out of the circuit. There's got to be some way to disconnect it and just have the run winding operating. That's the whole idea we have with things like a centrifugal switch, or with different temperature sensors and temperature relays that we can use, and things that are going to be sensitive to current level and all sorts of different ways that we can make sure we disconnect our start winding. Why do we need to disconnect our start winding? Well, because the start winding has more windings to it, which means it's have more wires. Well, it's got more wires. That means it's going to be consuming more electricity, and it's going to draw higher amperage. We need that high energy and amperage when we're starting the motor to overcome that initial lockup that the motor has when it's sitting there still. When it first starts up, it needs a lot of energy. Once that energy is there, it'll move, and it can cut back the amount it needs to move, and it can just use the run windings on these single-phase split motors. So usually a capacitor is a really easy way to try and control that, depending on the motor. For a permanent split capacitor motor, that's the one exemption to this whole rule, though, because they have it where the capacitor will generate and reconnect the start windings when it needs more energy in order to keep the motor moving. in case there's a lag or a buildup of amperage or a slowdown of electric flow. It can basically get more juice into the system through a capacitor. And that's what you're going to be seeing a lot of times for those motors. So, like I said, a couple of different styles of starting relay types we've got. We got current, solid state, potential. The main thing is voltage is going to be the amount produced in the start winding, all right? Back electromotive force, we're talking about voltage amount produced in the start winding. So how much energy is going to be needed right at that startup? That's what it's needing. That's that back electromotive force. Remember, electromotive force, that's just a fancy way to say voltage. So back voltage is the amount produced in the start winding. It's going to be that really high level of energy that's required when it starts up. So current or amperage relays, they're your most basic style for a single phase motor. It's got it where it does the easy thing. It's going to have it where it's going to sense the current or the amperage of the motor, and that's when it's going to decide when to disconnect that starting amperage. Because again, or the start winding. Because again, remember, starting amperage greater than the running amperage. Your running amperage is stated as your FLA. That's pretty much all you're going to be seeing it written as nowadays, is the FLA of a motor. Typically, your starting amperage is going to be about 5 to 7 times greater than your FLA. Not always, depends on the manufacturer. Sometimes they make them where it's going to be, 10 times greater, that starting amperage, and then it's going to cut back to a really, really low running amperage. You're seeing it more nowadays where DC electric motors are becoming commonplace, and they run on inverter technology, so they can vary their speed, but they're still taking in a lot of electricity. They're taking in a lot of AC electricity and converting it to DC. But the ability to control the speed and vary it is what makes them more energy efficient. So the current or magnetic relay, basically, once it's about 75% of the speed the motor's up to, it's going to disconnect that start winding. It's going to see the amperage. It's going to check and make sure. And when it sees that high amperage, it's going to know, okay, well, if we've got this high of amperage, then I know that the motor's up to this a certain amount of RPMs or speed, and we can disconnect the start winding, and the run winding will be able to take care of this for the rest of the time. And that's basically what that's going to do until that speed drops or anything like that. If that happens, then it'll try to re-engage your start winding. So again, operation of a current relay, much like a solenoid, which you can see right here. We've got it where there's this electric coil. You've got power coming in, power going out, and it's going to basically, when that power runs through there, it's going to pick up a little bit of it. It's going to see, okay, how much amperage are we having through here? And that amperage and that electricity will build up and will disconnect and not allow power to pass through to the start winding after a certain amount of time, or once it gets to a certain amperage. That's the whole idea behind it. So speed increases, amperage decreases, and you're going to have it where that motor is just going to be able to just disconnect because you've got lower amperage, and it'll allow it to the start winding to be disconnected from everything. And then you'll just have the run winding going. So that's the whole idea behind these, really. Again, current relays, most are easy to troubleshoot. Yeah. You just basically make sure that it's opening and closing. All right. With most relays, that's what you're going to be looking to do. You've got to make sure that they are allowing power to pass through when they're supposed to, and they're stopping power from passing through when they're supposed to. Basically, how are they operating? Is the switch opening and closing? Because that's what a relay is. At the end of the day, a relay is simply a modified, sophisticated switch. So having that as an option, having that as the the main way that we're going to have a control over our winding, it makes sense to have an automatic switch as opposed to having to have some sort of manual control or some sort of really complicated digital signal or app controlled kind of thing. They've got it nowadays where there are systems that run where they've got basically some microprocessor controlling all this kind of stuff, and that runs like a computer. But the problem with it is it's not as easy to repair. You've got major computer parts and everything like that, and it's much more expensive. So you're going to see current relays and these kinds of components used more often because they're cheaper, because they're easier, and because they work just as well. The difference between these kinds of components compared to those expensive ones is that the expensive ones are more energy efficient. That's really it. And they're only energy efficient if other factors have been played into it, as far as insulation of a building, insulation of windows, what's going on with the attic and the crawl space, and what kind of flooring are you using? What was the material used as far as the outside of the walls? Is it brick? Is it a wood frame? All that plays major factors into it. But most people, they don't care about that. They're not worried about that. So all they're going to do is they're just going to get the cheap unit that, hey, it passes the code and it's the cheapest one they've got on the market, and that's what I want because I only want to pay, $100 a month for 10 years, and then I've got a new system. Because that's usually what people will do. They'll take out a 10-year payment plan, and it's about 99 to 100 or so bucks, and they'll be able to pay off, and they'll have an entire HVAC system brand new installed for them. So it's not the end of the world when someone loses an HVAC system. Never think that it is. It's just part of life. You're gonna have to replace it. So having cheaper parts and things like that, components like this, it makes it so that you can make a system last longer because you replace more components. When you get those sophisticated board control systems, you've got it where now it's going to be $500 for a single board, and that's the only part that I can replace. So every time something goes wrong, it's a $500 part bill automatically, almost. So that's something that can happen or occur. And I've done that before. Luckily, most of the time when there's a board failure on those newer systems, that in my experience, it's been when the systems are newer, they're still under warranty and everything. But people do not want to pay, because I remember it was a $900 carrier board is what I had to install. It was $900 on my cost as an HVAC technician with a pretty big company. We had it where it was $900 for us to get that board still. We were a carrier dealer. Like, it was crazy, but that's what you deal with. So again, other thing is going to be controlling our electric motors and components and everything like that. Potential relays. These are getting more and more there. They're having it where it's being used on a lot of these newer systems where they're not putting it all on a control board. They're putting more mechanical components. Train XL units, they use a lot of potential relays, and you're going to see it used for walk-in coolers as well. These are pretty common for both of those applications, just because basically the whole idea is we're going to be disconnecting our start winding. We need a way to be able to do that very easily, and this is just literally reading the voltage. So it makes a lot of sense. If it's just reading voltage, then it's going to be able to tell when and if we need to disconnect or anything like that, and it'll just be able to, okay, yep, we're good, let's disconnect, and we're getting power to the system. Motors turn as it should be. Start windings, again, remember, they're going to be taking in all that extra power, and they're going to be, bringing in all that electricity into the system. That way it can start up, So the potential relay opens when the motor reaches a certain back electromotive force. When it's got that back voltage feed from that start winding and everything, it'll decide, okay, yep, we've got enough. we're good. Let's go ahead and, you know, disconnect that start winding, allow the run winding to take over from here. So basically, how much extra power are you producing more than needed? That's what it's going to look for. That's the whole idea with the potential relay. Again, it makes sense. Contacts are normally closed when unit starts because it's going to be starting up the system. And it's part of that start winding. So the only problem with it is sometimes is you'll have it where there are some relays that will be time delayed or temperature delayed that you'll have a motor and, oh, the fan motor's starting but the compressor's not. Oh, that must be a bad compressor. Keep in mind, we've got relays that disconnect just because of the compressor getting too hot or not enough time going by between shutdown and turning on. So we got a lot of different ones. Potential relays, again, similar to pretty much any other relay we're going to be seeing. You've got your terminals that are going to be located all throughout the relay, and depending on which style it is and everything like that, they'll tell you what to connect to each terminal as far as which are high voltage, which are going to be power in, which is going to be power going out, all that kind of stuff. So really, you're just going to be checking to make sure that power is passing through, and you're going to make sure that the coil is working properly, and that's it. Yeah, they're very, very simple. It's just like any other relay or any other contactor or anything like that we have. It has a coil. It's got its terminals, and you're just making sure that the contacts are closing, that the terminals are having energy provided to them, and that we're not having a system just completely malfunction and fail on us, basically. So that's what you're seeing a lot of times nowadays is these relays being used all over the place because they're easy to troubleshoot, and replacing them is cheap. They're like maybe $15 most of the time. Some of the newer, fancier ones might be like 30 or 40, but still, that's nothing compared to the price of, a couple $1,000 for a compressor, thousands of dollars for, some motors just because of how hard they are to reach. And it'll take extra labor just because, we have it where, well, we can't get to your fan motor without having to, disassemble your ductwork or something like that. So that I've run into before, and it kind of sucks when you get to those situations because it's what we're doing. You end up doing almost the entire job of like a complete install, like replacing a heat exchanger, when it would cost them almost not that much more to get a whole new system. And that's when you got to talk to customers and just be honest with them and let them know. Be like, hey, look, at the end of the day, here's what I'm doing. This is another repair, but if we really want to get, the best option for you, you might just want to go with a full system replacement at this point. All right, so solid state starting relays and devices. We've got a couple of different ones we're going to be seeing. So solid state starting relays, again, used to drop out start windings. What's talking about solid state? What the hell does it mean? Solid state starting relays. We're talking about solid state devices. You guys have seen solid state devices all your life. You've seen them all over the place, and you use them pretty much every single day. It's control boards. All right, that's all that means. Solid state devices is a control board or a microchip board or something like that, where it's got transistors and resistors and all those different components on it. It's got diodes and relays all over it, and it's the most common thing you're seeing nowadays because everything's switching to control boards. You do not see a single furnace or air conditioner nowadays that does not have at least one type of one part of it is solid state starting relays. As far as modern systems, yeah, you might go to someone's house and the house was built in the 1970s and they still got all relays and mechanical parts and components with no control board whatsoever on maybe a furnace or a really old air conditioner, but it's very rare to find that. So these are nice and easy because they're going to be more accurate. They're going to be more they're going to have more accuracy of control and ability to get the most efficiency out of our motors, because the motor is the major load. It is the biggest thing that's going to consume energy. It's also going to be the most expensive part to replace. So if we have it where we can make sure that that system is running and operating at its optimal level at all times, then that's ideal for us. And it's just a matter of, using these kinds of devices to their best ability. And they're getting more and more integrated into the parts and components. You're going to see it where everything eventually is just wired back to a solid state device. So permanent slip capacitor motors, this is your most common, especially in residential, for compressors, condenser fan motors, your blower motor, your inducer draft motor. They're all going to be PSC motors just about on most systems. Again, depends on what you're working with and what kind of electricity, but for single phase systems, it's a very easy type of motor to operate. It requires very little maintenance. It's not that finicky, and replacement for the capacitor is common, easy, and cheap. It's not an expensive thing to do. It's you get a new capacitor usually every couple of years on an air conditioner, and it's only going to cost you about $150, so $50 a year for maintenance of your motors, basically. Now you could have it where you don't have where it could go longer, but you got to do more maintenance. Then you're going to be making sure that your coils are clean and making sure that your filters are always changed, making sure that your blower motor is not covered in dust and everything like that, taking off your control panel and inspecting everything, looking at your electrical wires and making sure that you have good connections, checking and making sure that nothing is getting damaged. When you go outside and you're mowing the lawn or weed whacking and you're right next to the air conditioning unit, you need to make sure that if anything flies up by that, your wires are protected. So maybe buy a new piece of conduit, which is way crazy. Nobody does that, but maybe someone will. I don't know, to protect thermostat wiring because it's important. So all these kinds of things for a PSC motor system makes sense when it comes to residential, because when it comes to residential, you're usually much more limited on funds than you are for a commercial or industrial situation. A commercial business gets told, hey, you got to get a new air conditioner and it's going to be, $15,000, $20,000. And they're like, okay, yep, that's expected. Like that, we planned that, an air conditioner is eventually going to go out. We have that as part of our budget, as part of our maintenance is, such and such amount of dollars. Now, yeah, it probably eats into it, as far as their whole year's worth of maintenance budget. But if that's what it gets to the point of, that's what it gets to the point of. But if it's, for them, it's also, let's not use the PSC motors because I'm not going to have that $20,000 bill. I would much rather have the $2,000 or $3,000 or $5,000 bill to replace the whole compressor, and that's what you see more and more often with a commercial setting. Is it's going to be that kind of mindset of, okay, well, yes, a new system is much more, but I'm just going to let this, I'm willing to pay a quarter or a half of a system because I've got the money for it, and I've got a budgeted plan. I don't want to eat my whole budget up just because, oh, your compressor's out. And on a residential system, that usually eats up their whole, amount of replacing the system. And for you, it'd be, a quarter of it. And they're like, no, I'll just pay for a quarter of the system, basically. So that's what is, pretty common as far as mindsets you're going to see seeing, in my experience, at least. So solid state starting relays, again, they're going to be in series, low resistance, very, very high controls. You're going to have, basically, it's going to allow for current to flow where it needs to go. When it needs to go to the start windings, when it needs to go to the run windings, and it's going to make the main decision for where energy is going to be headed throughout a motor startup and throughout a motor run. So Again, super easy to troubleshoot. Biggest thing you're going to be doing is using an ohm meter. Look for your check for resistance. Make sure it's it's either, if it's supposed to be open, it should be open. It shouldn't have any, it should be OL on your meter for resistance on your ohm meter. For a normally closed one, it's going to be close to zero is what you want. You want very, very, very low resistance across that relay. So visible signs, again, easy. That's the easiest thing, honestly, with these boards is you just look, you'll take a panel off, you will smell an electric burn smell, and this is when it's really, really good to have a nice little flashlight. You can get a Mac light for like $8 down at the store, or less. I think you can get it for like $5 if you go to Harbor Freight. They are fantastic. You take them in, especially when you're looking at a board in an attic, you're looking at a board down in the basement, you're looking at a board in the middle of the night on a condenser coil because the air conditioner went out. It's 90 degrees, 90% humidity that night because it's Virginia, and that's what freaking happens. We have those crazy hot nights that just, oh, is it going to get cool tonight? Nope, it's just going to stay hot and humid. So people are going to call you out there in the middle of the night, and they're going to want that AC fixed. And having a good flashlight, I know this sounds weird. It's like, why would I? Trust me, it makes it so you can go over the good details of it. Something other than your phone. Do not trust the flashlight on your phone. It's bulky. It gets in the way. You have to peek around it and everything like that. Having a small, thin flashlight or even the LED flashlight that y'all have in your tool bags, that's a really good way to actually just look at the board and physically see anything. If you see burn marks, it's done. There's no question, it's done. That's it. You got a burn mark on a board, it's done. There's no coming back from that. It's so precise, it's so accurate as far as how it's designed and controlled. You cannot repair them. It's much, much easier and cheaper to just get a new one. The problem is when, like I was saying, it's 3 in the morning and it's real hot and you just went out there and then you got to tell them, sorry, can't do anything until we get some parts. Because you might not have that board on your truck. You might not have that style of system or anything like that. So you got to just, wait until the parts open up or tell them, yeah, we can get emergency parts, but it's going to cost you an arm and a leg, for a control board. So it's up to the customer always, though. Provide them with all the options. Never leave something off the table for them. Let them know what all their options are. Motor bearings, this is your most mechanical part of your motor. Bearings are going to be in just about every single type of motor. They're going to be in wheels and tires and all that kind of stuff. You've probably seen them in something like that if you ever worked on vehicles. Vehicles do have bearings. But for us, bearings most of the time, for residential systems, they're not going to be replaced that often because they're usually come with or part of the motor. And the amount of time to take off a bearing, put a new bearing on, make sure it's repacked perfectly tight, right back into the same part and everything like that. It can be a little more time consuming than just replacing the whole motor because they come pre-assembled with their bearings. When you get to commercial and industrial level, you're going to see it more often where a bearing gets replaced. That's when you're dealing with more of these large ring bearings right here. This is more of your residential style, about the biggest you're going to be seeing for most systems as far as fan motor bearings. But this is more of your commercial industrial style. And just making sure you get the right style of bearing, make sure you get the right size. That's the important thing when replacing them. It's a pretty common thing to do as far as motor repairs and maintenance, to replace the bearings for commercial or industrial. For residential, it's just replace the motor once the bearings go out usually. Unless it's got an area where you can re-lubricate the bearings, and that's all that needs to happen. That's all you need. So bearings, basically, they're the part on the end of the rotor, at the ends of the rotor, that allow for the rotor to rotate smoothly. Those smooth balls, that greased oil and everything like that that's going to be in there, that allows for smooth rotation continuously. So ball bearings, they're definitely our most common one, or one of the most common ones you're going to see for a lot of motors, because they're just easy. They make sense. They're very common. The problem with ball bearings, and they can handle a high load. The problem with the ball bearing system is it's very loud. So compared to sleeve bearings or something like that, which, funny enough, that's what we're talking about next. So sleeve bearings, this is what we're going to see more often. That small ring that I was showing 2 slides ago, that is used in residential systems, that is your sleeve bearing. It's usually going to be lubricated from the factory and everything like that. It'll have basically, and it's just going to be smooth metal that allows for good, quick rotation constantly throughout the system. So they're really, really versatile. They work really well. And the nice thing about a sleeve bearing is very quiet. So especially for blower motors and for motors for moving air inside of a building, a sleeve bearing makes it so that it moves the air quietly, or more quietly than it would if it was a ball bearing motor. So 2 different styles of motors we're going to have is either direct drive or a belt-driven motor. So this picture here, this is a belt-driven motor. You have your motor located here. All right, power is going to come into this motor. It's going to spin this pulley, or spin this wheel, and then this pulley, all right, this belt, that's what we're going to have working. And then that belt is going to pull this wheel, and it's going to spin, and they're going to spin together. And depending on the distance that they're at and the tension of this belt, you can adjust the speed of this wheel here. Tension on that belt is also very important. But the other style we're going to have is where basically instead of there being this belt, this is what you've probably seen in the classroom more often, is where the motor is basically sitting right here. It's directly connected to the blower wheel inside of the blower motor, and that direct connection is a direct drive motor. Direct drive motors, again, they're just going to be basically mounted directly to whatever it is. It can be directly mounted to a pump system. It can be directly mounted to a fan blade. Those are your most common that you're going to be seeing. And that's basically what you've got going on for a direct drive motor. So again, motor drives, if it's a belt system, it's a V-belt. That's what you're going to be using. You've got 3 sizes usually, FHP, A, or B, and then that's pretty much what you're going to be seeing most often in the industry. This is what's used typically for rooftop package units. It'll be the motor itself will be on a track that you can loosen with the nuts on the bottom of it basically, and you can, as you tighten and loosen them, it'll move it forwards and backwards, so you can, bring it up, loosen the belt, take the belt off, put the new belt on, and then tighten it back into position and check the belt tension with a belt tension gauge to make sure that you've got proper tension going on in the system. So that's all there is for the components for electric motors. Again, just keep in mind there are a lot of different things. Make sure to read Chapter 9. It's got a lot of good information on all of these different relays. All right. Thanks, guys.